Okay, hi everyone, and welcome to the SETI Institute Lunchtime Colloquium Series. I'd like to thank all of you for coming today. We have a very interesting speaker today. We'll hear from Professor Ron Greeley from Arizona State. He'll talk about aeolian features on various worlds of the solar system. And I'd like to remind you that we have these talks every week, and I encourage you to attend them. Next week's talk will be a very different talk. It'll be more of a astrophysics talk by Joanne Hewitt, and the title is The Hunt for Hidden Dimensions. So another reminder is that we videotape these talks so that we can place them on our website. If you go to our website at www.seti.org and click on the picture of Frank Drake that says Scientific Talks, you'll get to the Colloquium webpage. And there you can download videos of all the talks in our series, and you can also see the schedule of upcoming talks. So because we tape these talks, we like to record the questions as well as the speaker. And so after the talk, I will, during the question and answer period, I will bring the microphone around to people. So please hold your questions until you have the microphone. And the microphone doesn't amplify your voice, but it will record it so that you can hear it on the video. So with that, I'd like to just give you a minute of background on Ron Greeley. He received his undergraduate and master's degree in geology from Mississippi State University and did his PhD work in geology at the University of Missouri at Rolla. He actually worked at NASA-Ames to help prepare for the Apollo moon missions. So he's been doing planetary geology since there was planetary geology. He's a professor at Arizona State University, where he's been since 1977. He has wide interests in planetary geology and aeolian features around the solar system. And he has served as a member of the imaging team for a wide variety of spacecraft, including Mariner, Viking, Galileo, the Mars Exploration Rovers, and Mars Express. And so today he'll give us an overview of aeolian processes on various worlds in the solar system. Thank you.
Okay, thank you, Cynthia. And do I need this, or is this doing the job? Great. Well, I'm delighted to be here. Thank you for asking me to come. It's good to see old friends and to potentially see some new friends and faces. And what I want to talk about today is this topic, planetary aeolian activity. And what you're looking at here, as most of you know, is a series of images that we took from SPIRIT that shows aeolian processes in action. This is a series of active dust devils sweeping across the surface of Gusev crater. And we'll look at that in a little more detail later. So here's what we're talking about in the planetary connection. Aeolian activity equals wind plus particles. So any planet that has an active dynamic atmosphere and a supply of loose particles on the surface is subjected to aeolian activity. And this simply shows the primary objects of affection for us and the conditions that are relevant for this process. Where do particles come from? The first requirement here. This simply outlines the sources of particles that are generated on some planetary surfaces. So that's the first requirement. And what we see here is the particle size distribution from different processes. And I'll point out to you that Mars dust, something that's a big focus in the Mars community, consists of very tiny particles compared to global dust on Earth. Mars dust is only a few microns in diameter. So it's very fine-grained material, as most of you know. The second condition is the wind. Now here's where there is often some confusion. Somebody will say, what's the wind speed needed to move sand? Okay, and somebody might give you an answer. But that single value doesn't really have meaning unless you place that single velocity in some context. Because as Bob Haverly can talk about, when we look at the boundary layer, that is when wind moves across a surface, the higher above the surface you go, the stronger the velocity. And of course, the closer you get to the surface, eventually the velocity is zero. What's going on? Well, in effect, energy is being removed from that moving air mass that's being transferred to the surface, and that's where the connection comes for aeolian geology. It's that transfer of energy from the moving air mass to the surface that's capable of doing work. What's the work? The work is moving particles, sand and dust and potentially larger grains, moving across the surface where it can erode, where it can be deposited, where it can alter the surface. So here are three wind velocity profiles. Here's a relatively gentle wind, and here's a stronger wind. So when you say what wind is needed to move particles of a given size, well, it depends on how high above the surface that single measurement is made. If it's the height of the Viking landers, it's about like this. Viking's the only mission where we've actually measured the wind speed. And we measured it at one height. So there's a fundamental problem here when we try to look at the physics of particle motion on planetary surfaces. The problem being we don't have very much real data. A couple of exceptions I'll talk about in a minute. Well, so it is this transfer of energy in the turbulent boundary layer of the atmosphere that is able to do work. And now we come over to the wind conditions needed to move particles of different sizes. And so ignore this part of the curve for a minute. And as one would expect, bigger material, sand to gravels and granules and so on, requires stronger and stronger winds. Sure, common sense. But now we also notice that very fine-grained material also takes stronger winds. And in fact, there is a size that's moved at the lowest strength wind, which is about sand. Well, what's sand? Think granulated sugar. Sand, fine sand. In contrast to dust, think baking flour dust. Now think really fine dust, really fine flour, and there's Mars, dust. Now, so this is called the threshold curve. This says what are the wind speeds needed to move particles of different sizes, all of the factors held equal, particle density and so on. Well, the term that's used is V star, and V star is not a true velocity. V star, or the friction velocity, is a function of the shape of this boundary layer profile, which on a log plot is a straight line. So when somebody says, what's the wind speed needed to move different particles, make sure that they understand and you understand this is what we're really dealing with, the so-called friction velocity. Okay? All right, so once the grains are set into motion, here's that wind velocity profile moving across the surface. What's the easiest particle to move? Fine sand. And that fine sand, sand in general, moves in a saltation trajectory from the Latin saltate, that means to hop. So here are these particles that are hopping along the surface, sand-sized particles. Some of those particles come down and splash into other sand and set them into motion. Other particles come down and splash into dust, the fine-grained stuff, and once the dust is up, then it's easy to be transported in suspension, the kind of atmospheric dust that we see on Mars, for example. Other sand smacks into bigger grains that are too large to move on their own, but they're pushed along the surface and creep. So particles are transported in saltation, suspension, and surface creep as a function of wind velocity and particle size. Well, what are we talking about for planets? Venus, of course, was imaged by Magellan years ago, and what we saw on the surface were various features that are related to the wind, primarily these various things called wind streaks. And these wind streaks gave the orientation of the winds at the time of the streak formation. Even before the mission flew, atmospheric scientists predicted Hadley cell circulation on Venus. What we did was map these features from the Magellan data, thousands of these features, and they act like little wind vanes. And what was the pattern that was shown? Hadley cell circulation. So this is how we can tie aeolian processes and surface features to atmospheric sciences in this case. Now we come to Titan and the so-called cat scratch features that are considered to be dunes. The point here is these features are also the result of the dynamic atmosphere on Titan interacting with particles of some sort, frost, ice, solens, whatever, on the surface where it's getting organized into patterns that, again, in this case, are indicating the wind directions. And so folks like Devin Burr and others and Ralph Lawrence are just getting into the analysis of these features and how they can be related to patterns on Titan. Even Triton shows evidence of aeolian activity, despite the fact that it's an extremely low density atmosphere. But the geysers that were discovered with Voyager decades ago, those geysers are also generating material on the surface that's being carried by the winds and leaving patterns behind. So even on this icy moon, there is evidence of aeolian processes. Mars, of course, is not only an area of great interest, but it is dominated by wind-related processes. Every place we look, just about every place we look, shows evidence of wind modification. We see the classic sand dunes, and I say sand dunes because the physics drives their formation only with the accumulation of sand-sized particles. We see from the rovers and other landers ripples on the surface and evidence of erosion of the rocks. And then we see features that Carl Sagan termed variable features, albedo patterns like these wind streaks that change their size, shape, position, occurrence as a function of time and in response to the wind. So we've known, of course, about dust for a long time on Mars, that dust is active. We see it in regional dust storms shown in this series of pictures. We see global storms that my colleague Phil Christensen's thermal emission spectrometer obtained this series of images over a period of a month that shows the growth of a global dust storm. And we saw local dust activity in the form of the dust devil. So at all scales, dust, the very fine flower-sized stuff, is active and has been known to be active for a long time. What about sand? We see some sand dunes, fields of sand dunes that have impact craters superimposed on them. Do you think those sand dunes are currently active with impact craters on top of them? Unlikely. In fact, they probably are old features. Those dunes have been stabilized for a long time. But that doesn't mean that all sand, the granulated sugar-sized stuff, is inactive every place. But this was a basic question. Well, we've answered that question now with MUR, with Spirit. And here's a view of the deck. Here's the scale. That's 1 millimeter. And what we see on the deck are sand grains a few hundred microns in diameter. How'd they get there? Saltation. They hopped up there. It wasn't launched with sand. Had to get there some way. And the inference is that it was emplaced by wind. And here's a before picture from Spirit. Here's an after picture. And what we see, in fact, we've looked at this very closely, we can see sand ripples that are actually moving in sequential images. And so we can now answer the question, yes, sand is also active as well as dust. Okay, so that sets the stage for how do we understand aeolian activity. And we do this through a combination, of course, looking at planetary data. Here's a series of wind streaks on Mars from the Viking mission. We do this with simulations where we try to duplicate the conditions, in this case, of Mars, using the wind tunnel that's over at Ames that can simulate Mars. So what we will do, though, is run an experiment in the wind tunnel under Earth conditions, 1 atmosphere conditions. And then we go out into the field and make measurements under natural conditions for Earth to test the validity of the simulation in the wind tunnel. Because if we can't simulate conditions for Earth, how much confidence is there that we're actually simulating Mars? Not much. So once we work out that we're doing a valid simulation, we can come back now and run the same experiment under Mars conditions, where the primary parameter is the atmospheric density or atmospheric pressure. Well, you can't simulate everything, of course, in the lab, and that's where computer modeling comes in. And so it's really a combination of all of these things to try to understand what's happening, the fundamental physics and science well enough to extrapolate to, in this case, Mars. So that's the approach that we use. Our lab that I set up when I was at Ames decades ago uses the structural dynamics facility in building 242. This was a chamber that was originally constructed in the 60s for testing of rockets. This entire chamber, 4,000 cubic meters, can be pumped down to 3.5 millibars pressure. And it's pumped down by using what's informally called the steam plant. That's this facility across the street. So the steam plant can pull the vacuum of this chamber to Martian conditions in about 45 minutes. And then we can run our experiments under Mars conditions with respect to the atmosphere. Here's a view taken from the top of the chamber looking down at the floor. This is the Mars surface wind tunnel that's used for our primary experiments. We also have the Venus wind tunnel, which currently is being retrofit to run experiments appropriate for Titan. We were through with the Venus experiments following Magellan. The system was mothballed, and then we're bringing it back up to simulate Titan. In the background is the Dust Devil simulator, and this is a system, because dust devils are important on Mars. We fabricated this, and here's a view of a dust devil on the tabletop of the apparatus. Okay, fundamental parameter, threshold, minimum conditions, move particles of different sizes under different conditions. Here's the shape of the curve for Earth. The classic U-shaped curve where the particle size that is most easily moved is about 100 microns. Here are the conditions from our experiments for Mars, the experiments for our conditions on Venus, and our predicted experiments for Titan. The shape of the curve is essentially the same. That is the optimum particle size, around 100 microns. Upturn in the curve, smaller particles are more difficult to move for a variety of reasons. But the position of the curve in relation to the friction velocity is offset by orders of magnitude as a function of atmospheric density. And so the process is the same, but because of the difference in environment, primarily pressure, to some extent temperature, there is this offset in the curve. Here's another way to look at that. For 100 micron particles, the optimum size, here's what the wind velocity profile looks like for Venus. In other words, the high density Venus atmosphere doesn't have to be moving very fast to do the job. There's a lot of air there. Here's the curve for Earth. Here's the curve for Mars. The very low density Mars atmosphere means that that air has to be moving very fast to transfer sufficient energy to set the grains into motion. Okay, now we come to dust devils. Dust devils, completely different story. And in this case, these have been talked about for a long time, back to the mid-60s, that maybe dust devils are important. They were discovered on Mars quite some time after the pictures were actually taken by Peter Thomas and Peter Girash on Viking orbiter images. And now all of the missions that have flown, except Opportunity, have shown dust devils, both from orbit and from the surface. And these are vortexes in the atmosphere. And here's an active dust devil seen in the Mach data. And here is the shadow cast by the dust devil. And from this we can measure how high it is, many kilometers high. Here's another active dust devil that's climbing up the wall of a crater and leaving a dark trail behind. And then here are inferred tracks left by dust devils in another area. What's going on? Well, from our experiments, here is the case for normal boundary layer winds, the kind of threshold curve that I showed earlier on Earth compared to the boundary layer condition on Mars. Here now are the dust devil data. And what do we find? Well, lower winds, effective winds, do the job from dust devils than for boundary layer winds, especially for the smaller particles. Here are the curves for both the vortex or dust devil machine and the normal boundary layer winds collapse. But it's the smaller particles where dust devils are more efficient. What's going on? Well, we've made measurements of the pressure distribution through the cores of dust devils in the laboratory and in the field for Earth. What do we find? The core of the dust devil is lower pressure. So, what's going on? It's sucking the dust up. It's acting like a vacuum cleaner. So here the dust devil is working across the surface, sucking up the dust as it goes, and leaving that dark track behind. And so part of the story here is that dust devils are very efficient in lifting dust, more so than normal boundary layer winds. So that's the message. Now we come to Gustav Crater, the Spirit landing site. Landed in this low albedo zone near the Columbia Hills. And the Columbia Hills are here. The landing occurred here, as you know. And of course, dust devils were seen. As a matter of fact, we have identified and gotten data on over 700 active dust devils from the 2 seasons of dust devil activity. And of course, that's the picture I showed earlier. This was very interesting in terms of the solar panels that were used to recharge the batteries. We saw a slow decrease in energy generated from the panels. Why? Dust was accumulating on the solar panels. Then suddenly one day, an enormous spike in energy. That same day, we saw in the pictures a dust devil. And so the inference is, wow, along came the dust devil and swept the solar panel clean, remained clean for quite some time. So the wind giveth and the wind taketh away in terms of dust, but not the second year. And here's a view of the dust-covered self-portrait of the rover. You can see all the dust on the panel. Why didn't the dust devils in the second dust devil season do the job? Well, let's look at the data. First of all, here are the main tracks in the first dust devil season. And here are the tracks. This is simply a function of viewing geometry. We're up into the hills, and so this is the field of view. Second dust devil season shown in yellow. Here are the histograms of the dust devils as a function of Sol for the mission, and more importantly as a function of L sub s. Now, in terms of L sub s, we landed at about this time here. toward the end of what would infer to be a dust devil season. So we were on the surface and then came back around, and now here we started seeing the dust devils pick up for the first season that was monitored. So they went through a specific period of time, late spring, early summer, and then none. And then here was the second dust devil season, all right, occurring remarkably close to the initiation when the first season occurred. Now, here for those seasons is the temperature derived from test. Now, test was not operating concurrently with this, so we took the record as a function of L sub s from previous years and superimposed it on here. What do we find? Well, it's not so much the absolute temperature that's important for the growth of the occurrence of dust devils as it is the gradient. And so the surface has to be being heated up for the dust devils to occur, and then when the surface cools off, the dust devils decline. And so with this in mind, of course, here is the dust devil season. Where are we today? Today we're right in here, and I'll come back to that in a moment. Now, here's the atmospheric opacity superimposed on this. Here's the second dust devil season, and look, this is a very dusty period in comparison to the first season. So we think that this abrupt truncation of dust devils correlated with the lot of dust in the atmosphere could explain why the dust devils shut down. What are dust devils? Dust devils are driven by heating of the surface, a change in heating, not the absolute temperature. And so the idea here is the dust in the atmosphere caused a relatively uniform temperature over the surface that caused those changes in temperature to be shut down. And so we think that is partly why dust devils didn't continue and why the dust devils didn't sweep the rover free of dust in the second season. Now, as I said, right now we're right here. Unfortunately, the start of the second season occurred during solar conjunction, so we couldn't take any data. When we came out of solar conjunction, of course, Spirit is literally limping along because of problems with dragging its wheel and so on. And the power is very low because the dust is really accumulated a lot, so we don't have much data. But we have just downlinked some of the data coming out of solar conjunction, and yes, we are now seeing some, again, active dust devils. So it falls right in here in this period when we expect dust devils to begin. So from a predictive model, we think for Gusev Crater anyhow, we know when things are going on there. Well, we've been able to collect a lot of data from the observations of the active dust devils. We can see where they are by navigating where they occur. We can get their velocities and other factors that are important in trying to calculate the flux. Question? Sure. Yeah. Differential heating. Heterogeneities on the surface. If we look at this on Earth, you know, it would be a little bush over here, shade, an area over here that has a lot of rocks on it, and so temperature difference right on the surface locally, in part, is the driver. You can't see that from orbit, but yeah. Yeah.
I would actually infer that it's not just the gradient. You say it's the gradient, not the absolute temperature. It seemed to me it was a combination of the two.
Yes.
Because it started, the gradient went up, but as the gradient stayed the same, as the temperature got higher, the frequency got higher, and then the gradient.
Yeah, you're right. You're right. Yes, I oversimplified it, but yes, it's both the absolute temperature and the temperature gradient you would maintain. Good point. So we're really interested in how much dust is being lifted in a dust devil, and this simply outlines how we get at that by looking at the atmospheric opacity in the dust devil and then working with our atmospheric colleagues to get at how much dust is being lifted in an individual dust devil. This is the kind of the bottom line here. For the dark areas where all the dust devil tracks occur, these are the statistics, and the sort of the bottom line here is that over this period of time, about 2 microns of dust was removed from the system. It's equivalent to what? About a monolayer of the dust. Some of it fell back down on the surface, but remember it goes into suspension and was carried away from the area, probably even out of Gusev crater itself. Now, we've also, through the capabilities of the German camera on Mars Express, which is a 9-line CCD system that has the 9 lines as it flies across the surface, gives us the chance to see features sequentially. And so we can track active dust devils on those individual lines and, of course, get the velocity of them. So we're beginning to apply some of the same things we have done from the lander to what we can see from orbit. And from orbit, we see all these marvelous tracks left by inferred dust devils. And, of course, we can see in active dust devils in the shadow the track that is, in fact, left behind it. Some of the tracks we find in these interesting curlicue patterns. And so we ran some wind tunnel experiments with our dust devil machine, and what we found is there's a very distinctive pattern of superposition of the track elements that tells us which way the dust devil is moving, even after it's gone. And so from those experiments now here on Mars, we can see that pattern, and then from that we can figure out which way it was going. And in turn, we can relate those things to models of the atmosphere, the kind of work that Bob does, and others that predicts what the general wind patterns are. So this is tying wind tunnel work to the analysis of the data. Of course, we started this work years ago in looking at wind flow around craters. And this is a series of experiments of flow around a crater and the distinctive pattern of erosion that occurred. Here's another run here. And then here it's compared to Mariner 9 data. And here are these ears that correspond to erosional ears here. And with time, eventually, all of the loose, bright sand is removed, except in very distinctive zones where it remained. Again, we compare to the Mariner 9 data. And so we came up with, and then using our standard approach, we went into the field and looked at natural craters on Earth for the patterns of erosion, wind scour here, and deposition, accumulated sand in these 3 cases. And then came up with this model of what flow around a raised rim crater would be, and the term that's used is a horseshoe vortex wraps around the rim of the crater and creates the distinctive zones of erosion and deposition. And so this comes out of the wind tunnel work. Now, what I want to talk about a little bit is how the lab at Ames is used to support flight systems. The facility is used not just for the science stuff that I've been talking about, but it's also used to develop and calibrate instruments that fly. Systems for EDL on the landers, for PATHFINDER that we did, for example. We developed the WINDSOCK experiment that I'll show you a picture of in a minute. We've done tests for rover where the HAZCAMs that are fairly close to the surface, the concern was, would those cameras get sandblasted? Would the lenses be no longer useful? So we ran a series of experiments to test that. we ran experiments related to Phoenix, and today, as we speak, as a matter of fact, we're running some experiments for MSL. What this shows is some experiments we did with JPL to look at the issue of forward contamination. And so if a spacecraft goes to land on Mars and it has bugs on it, and no spacecraft is ever completely clean, then if a wind comes along, what are the conditions where those bugs will detach? And if they detach by the wind, where are they going to go? And if this were a problem, then these might be places where you wouldn't want to sample, either for biology or for geochemistry, for that matter, with non-bug contaminations, but geochemical contaminations. All right. So we ran experiments to address that problem. Our experiments were one half of the approach, where the other half was done by JPL and Caltech people who had computer models to predict this. So they'd run the computer model, we'd run it physically in the wind tunnel, and iterate the results. So one simple test that was done was in the computer modeling, the folks used the old threshold test. In other words, what wind is needed to move particles of different sizes based on ours and other work. But all that information was done for geologic considerations. That is, sand and dust on the surface of a geologic surface, not a wind tunnel, not a spacecraft. And so the first thing we did was take the standard threshold test. Here's a little patch of particles on the wind tunnel floor with a thick bed of particles, a bed with just a few particles on the surface, particles that were placed on a glass plate, and then particles that were placed up on the top of a stylized spacecraft. And here are the threshold tests. Well, here's the standard threshold curve for geologic materials. Here it is on a rough floor, here it is on the microscope slide, and here it is on the top of the lander model. What's it show? Significantly lower winds can detach particles sitting on top of a spacecraft. Why? First, because it's up higher in the boundary layer and the winds are stronger, but also the particles are on a nice smooth surface. And so they're much easily removed. So the models had to be adjusted to take this into account. Okay? And so the point here is contaminants are much more easily removed from smooth surfaces up in the boundary layer than they are on the surface itself. We did other experiments for them as well, but here I want to change direction now and talk about the Mars Pathfinder WINDSOCK experiment that we designed. And here is our experiment sitting on Mars Pathfinder. And what this consists of are 3 dingle bobs, little cone-shaped devices that are free to move in a WINDSOCK in any direction. So if the wind is blowing in this direction, all right, there's the wind direction. If it's a gentle wind, it blows just a little bit. If it's a strong wind, it goes out a lot. What are the data we collected? We took a picture of it. And so by taking a picture of the orientation of the dingle bob, we could tell which way the wind was moving and how strong the wind was blowing, all calibrated in the Mars wind tunnel. What's the advantage here? Unlike Viking, we had measurements at 3 different heights. And the whole staff here is about that high. So we were getting a profile of the boundary layer. First time it's ever been done. Okay, because Viking measured 1 height. No other Mars lander has measured the wind speed. Now, you can pick this apart because, well, obviously the solar panel and the airbags and so on interfered with the local wind, but it was a measurement. Okay? So my plea is, if you are proposing a new mission or instrument for Mars, let's get some boundary layer profiles, Bob. Okay, this simply shows some of the experiments were done for the HAZCAM for MER before launch. The concern here was that flow around the model. The HAZCAMs might be sandblasted, but we're also interested in the pattern of erosion and deposition that would take place as a function of the lander itself. We also wanted to see where on the deck particles would accumulate. So we've used the results from those to analyze the data we've gotten. And then these are experiments that are going on now. We have a run that's underway. We'll be wrapping up in about 20 minutes for MSL. And basically, here's the deal. When MSL comes down, the retrorockets are firing to bring the lander down. Those retrorockets are impinging on the surface. What's happening to the surface? Will the rockets excavate a huge crater and cause the lander to fall over? Or will the material that's being kicked up from the retrorockets spray material that comes up and lands on the deck, clogging stuff? What'll happen? So experiments like this were done for Phoenix. Turned out not to be a big problem, but MSL is a much bigger system. And so what they're doing is trying to see what the predicted ejecta from the descent will be like. Again, they're numerical models, and we're checking those against the experiments that are being done here. That's what this represents. John Marshall is involved in this too. So, last line. Who cares? I care, but you should too. And first, aeolian activity is the dominant process on Mars today. If we think of all the possibilities, yes, volcanism could occur, yes, Marsquakes could be occurring, but we know wind is active today, and we can see the results of it. It's likely that wind has been active throughout Mars history. And so when we look at the longer-term effects of sand and dust, erosion and accumulation on the planet, it's part of the surface history of the planet. We see things result from erosion, from deposition, and then the wind streaks. And then this helps us tie what's going on with the surface with the atmosphere. And you have to keep in mind also that this has an influence on remote sensing of the surface. When we look at surface compositions, are those compositions indicative of the bedrock or what my geochemical friends call the surface scum, all that nasty sand and dust? So when we talk about remote sensing data, we have to be mindful of what it is we're actually looking at. And I believe that's the end. Thank you.